What is light? Wave theory of light and origins of ether in science.
Book description. Do you know what light is? Probably no one does. Nature of light has been one of the biggest mysteries of science for centuries. Is it solved today? Or have we simply assumed that we know enough and have stopped questioning? You may have learned that light is made of photons. You may have been taught that light is both a wave and particle, depending on how we look at it. Light is often described as traveling through a vacuum as tiny bullets, and a vacuum is an empty space of nothingness. This is how light is typically described and understood today. Yet, this understanding is not perfect. The scientific discoveries of the past couple of centuries have consistently pointed toward a different reality about light. Light can only be described as waves because of its unique properties, and these waves propagate through an all-pervasive medium called ether. If you are interested in the mystery of light and ether, you will find this book an excellent resource because it offers a unique combination and a fresh take on old ideas and discoveries that cannot be found anywhere else. Introduction. Light is a wave. We are going to explore why this is true and what it really means. Waves are patterns created when a cyclical motion passes through a medium. If we describe light as a wave, then there must be, by definition, a medium in which these waves propagate. Much as waves on the ocean propagate through the water, but whereas ocean waves crash on the shore, waves of light extend indefinitely. Thus, if we can see light coming to us from every corner of the universe, then the medium of light must be extended everywhere. Early theories of light refer to this medium in which light travels as luminiferous ether, and the entire unbounded ocean of ether was described as the plenum. It is this theory of a medium of light that this book explains and justifies. Ether is so fine in its constitution, intricate in its function, and pervasive in its existence, that it fills the space inside and between atoms, molecules, your body, planets, stars, and galaxies. The night sky looks like a dark empty canvas dotted with tiny shiny objects representing isolated stars and planets, but by understanding the true nature of light and ether, your mental picture changes forever. Ether is the medium of light, and the entire material world exists in it. The light of the cosmos passes through a great ocean of ether to reach you. You are able to see these planets and stars because you are connected to them through the plenum. This is a bold conclusion because we are living in a world where the corpuscular theory of light, the notion that light exists as a particle, has reigned unchallenged for nearly a century. So, rather than simply present a theory, an understanding of light, this book will take you on a journey through the historical evolution of our understanding of light. The heroes of the story are the many scientists and philosophers who devoted their lives to observing and recording, theorizing and experimenting, striving to bring us closer to a full understanding of how light works, among other mysteries of the physical world. To understand these findings, We must also understand the professional experiences and personal quirks of the people behind the science. My hope is that this detailed history of our understanding of light and the thinkers behind it will provide a new perspective on the physics of light, and perhaps reveal something about the human side of scientific inquiry. For those already familiar with the history and the science, I invite you to skip ahead to the final section of this book, where I present my own hypotheses and musings in the form of queries. A history of contributions to understanding light. How we came to our current understanding of light is similar to the story of any scientific inquiry. It is the result of generations of thinkers inspired by the world around them and responding to the ideas of those who came before. The details of these questions and the theories, experiments, and innovations they generated are unique in every case, and it would take volumes to describe the ingenuity of the individuals involved, and still more to understand how their personal lives influenced the course of their professional career that included groundbreaking discoveries. It is the purpose of this work, then, not to tell the whole story, but to tell a version of it. We will explore each step of this centuries-long discourse, taking major contributions and their relevant work as the focus of each section. And my hope is that this will at least provide a valuable summary of the vast history and science involved. Beginning with experiments that employ the modern scientific method, we will explore how light is understood as a perturbation of ether and why it behaves as such. This theory was first demonstrated geometrically by Christian Huygens in the mid-1600s, and then mathematically by Auguste Fresnel in the early 1800s. The wave theory of light has been through many speculations and challenges over the centuries. Yet the core argument persists as the only reliable model of light that is supported by numerous experiments. Fresnel described light as a two-dimensional oscillation of ether perpendicular to its propagation, and explained the polarity of light for the first time. The Huygens-Fresnel wave theory of light is the pinnacle of natural science. Light is electromagnetic in nature because ether is the origin of electricity and magnetism. In this book, I briefly touch upon the link between the origins of ether and electromagnetism, starting with the works of Ampere. The pioneering research by Gauss and Weber was a major affirmation and extension of Ampere's law. Weber also measured and hypothesized the units of electrical current and the relation between the speed of light and electromagnetic oscillations. Maxwell constructed a mathematical model based on an electromagnetic fluid and showed that the transverse oscillations in this hypothetical fluid will propagate with the speed of light. We will explain why and how Helmholtz supported Maxwell's theory and contributed to its development and acceptance. We will explore several historical lineages of research on electricity and magnetism, and some challenging aspects between them that remain unsolved to this day. Despite all the advancements in our understanding of light and ether, A sudden shift in the narratives brought the research of ether into a halt. To explain this shift, we will dive into the problem of stellar aberration, or our relative motion compared to a fixed frame of reference in the universe. We will re-examine the meaning and interpretations behind several physical theories about relative motion of objects and light, including Fresnel's partial drag formula and Stokes' alternative fluid mechanical model. We will explore some details of important experiments done by Fizeau and Michelson-Morley. We will expand on the ideas behind the interpretations and clarify some historical confusions that led to the erroneous omission of ether from the scientific scene. A clear experimental and theoretical foundation for understanding the partial drag phenomena was proposed by George Sagnac at the beginning of the 20th century. At the same time, Einstein proposed his special theory of relativity that was based on the assumption that ether does not exist. In Sagnac's model, waves of light move in the absolute etheric reference with constant speed, but we observe their superimposition in our relativistic frame as an external phenomena, which Sagnac calls external relativity. On the other hand, in Einstein's model, ether or the absolute frame of reference does not exist. To extend his interpretation, Einstein had to include a general transformation that could justify the constant speed of light for all arbitrary accelerations or rotations in all frames of reference. This led to use of a specific geometry in the general theory of relativity that necessitates the existence of an absolute frame of reference. This frame of reference is known as a spacetime. Just as bubbles on the surface of an ocean are tiny extensions of the ocean itself, atoms and all the physical matter that constitute our visible world are only a fractional manifestation of the ethereal world. This has been suggested by scientists for a long time, but evidence in support of this view was rediscovered and proven by the development of quantum theory, though not officially admitted. One of the aims of this book is to demonstrate that within the past several centuries, natural philosophy and science have had a love-hate relationship with the idea of ether. We are told that the theory of ether was objectively discredited at the beginning of the 20th century. However, the argument against the existence of ether is not convincing enough. Every time the idea of ether is denied, it soon reinstates itself with more evidence. Today, physicists entertain themselves with ideas such as duality of light, dark matter, dark energy, black holes, Big Bang, God particles, etc. All these fantastic and extravagant amusements are generously proliferated in the name of science, turned into books and documentaries and taught at schools. But any proper explanation of ether and its long-standing status as a valid scientific theory is rare to come across. This book is an attempt to remedy this omission by providing some ground for validating ether as a worthwhile theory in physics. I believe that there will be an ever-increasing interest in this subject. I write this not as a prophecy, but as an observation about a pendulum that has been swinging for many centuries and is inevitably swinging in favor of etheric sciences. There is one unifying concept behind all advancements and revelations in physics, and that is the honest effort to understand the nature of light and its carrier, ether. A careful examination of the historical development of science reveals this unifying thread. The concept of ether is intricately linked to the meaning of light, energy, heat, electricity, magnetism, atoms, quantum, plasma, gravity, and cosmology, but goes far beyond them. Ether is the elephant in the dark room of science. By confessing our knowledge about the true nature of light, we are unlocking the key to the uncharted territories of etheric sciences. There is much more to learn about the nature of light that I have not yet learned. I am indebted to the great wealth of knowledge that has been inherited from all scientists and seekers of truth in the past, and much grateful to the technological advancements that allowed me to access all this knowledge with ease. I praise in awe the future generations who will accomplish what is needed to complete our imperfect knowledge about light. Chapter 2: Light Through the Ages. Behind the meaning of light lies the meaning of our reality. In the philosophical traditions, light is associated with truth. In Plato's allegory of the cave, humans are kept as prisoners in a dark cave without knowing anything about the world outside. The man in the cave goes through 4 stages of liberation to finally achieve the realization of truth. First, he becomes aware of his situation in the cave by observing the shadows on the wall in front of the prisoners. Second, he removes the shackles, turns around, and sees the fire in the cave that is casting the shadows. Third, he ascends out of the cave towards the light of the sun. Fourth, the freed prisoner returns to the cave unable to see in the darkness and unable to convey his experience to other prisoners who are still arguing about the shadows. Plato never mentioned the fate of the man who returned to the cave. Let's assume that he succeeds in convincing other prisoners to at least try the first 2 stages. The third stage is the most elaborate one in Plato's allegory. Heidegger interprets it as, quote, the genuine liberation of man to the primordial light, close quote, which requires genuine effort and willpower to achieve. In the allegory, the primordial light is not the realization that our mundane occupations of everyday life are unreal. That must have happened in the first stage. It is not the liberation from shackles of the mind and society. That must have happened in the second stage. The light of the sun is perceived after the ascent from the cave. So until then, it requires faith that there is a true light to inspire the struggle to reach it by leaving the cave. Even after the ascent, more effort is required to adjust the eyes to more and more levels of brightness. But seeing in the primordial light is the ultimate experience in liberation. It is instantly known by the man in the allegory, without any further explanation, that he has seen the truth. There is no more doubt, no more struggle, no more imprisonment. The primordial light is a freedom gained by emerging into the realm of reality, of truth. However, by observing light from the more idealistic source, the sun, it becomes further away from the familiar sensation of light as we know it, the fire in Plato's allegory. What matters here for Heidegger is that experiencing the superior light source, the sun, forces the prisoner to question not just the differences between the kinds of light, but the nature of light itself, its essence and higher meaning. Open quote. With light and brightness we come again into the region of seeing, of the visible. What is visible through optical sensation are colors, glimmerings, brightness and darkness. Yet what is this brightness, light, and darkness? Certainly not a thing, neither a property of any kind of thing. Brightness, light, this is nothing which can be grasped hold of. It is something intangible, almost like nothingness and the void. Close quote. Heidegger acknowledges that there can be a theory for the physical reality of light, and it might be correct, but it can't be the truth. Heidegger's view is reminiscent of the Aristotelian argument in the sense that it acknowledges the deeper mystery of light, regardless of its physical mechanism. Some believe that there is an inner light and outer light. Inner light is the light perceived by you as your insight, including what you can see in your dream state. The inner light is linked to your imagination, ideas, and thoughts. The outer light is the unmistakable sunshine that you see and feel on your skin when you are fully awake. This is my naive and simplified version of entry into a long-lasting debate of philosophers over objective or subjective reality of the world. In other words, we must consider whether light itself allows us to perceive the world around us, or whether the world is brought to light by our perception. It would be deficient to pursue the outer manifestation of light without even mentioning the inner light. I wish we could have a lengthy chat by the fireside about which one of these, inner or outer light, constitutes our reality. You are welcome to reconcile this in any manner that satisfies your intellectual and spiritual taste. I subscribe to the idea that both are true, meaning that our reality is formed by both the inner perception and the outer physical reality. By virtue of our limited human existence, we are bound to live in balance between the inner and outer lights, and we must strive to integrate them. The search for the meaning of the outer light is a scientific endeavor, but at the same time it reveals a lot about how we think about and narrate our reality. The way we describe light is a reflection of us and our world. How we describe light is not merely how we see the reality, but also how we see ourselves. Remember that language binds us to the cave. Theories and descriptions talk about the shadows on the wall. If we go past the illusions into the realm of ideas, we may discover the flame that is at the source of the shadows. Still, deep inside, we know that there has to be a way to the primordial light. Let's hope that if we have a correct understanding of the nature of light, it will help us understand our nature and push away the edges of our expansive ignorance. The history of our understanding of what light means from a scientific perspective is in part a history of the thinkers who, fascinated by the mechanism of the universe, took to the study of light, bringing their own unique perspectives and insights to bear on the subject. An interested reader could research the current leading science on the matters discussed here, but they would only be receiving a limited piece of a farther-ranging discourse, much as the prisoners in the cave sees only a poor imitation of the sun's light. The story of light is not just observations and equations used to describe the phenomena, but also of the men and women who whose passion, curiosity, and sometimes faith led them to groundbreaking discoveries. Sometimes this appears as a smooth evolution of thought, but behind the scenes of objective, logical science are the hearts and souls of human beings. Even when building on the work of their forebears and contemporaries, the thinkers this book describes frequently disagreed on how to hypothesize, how to run experiments, and especially how to interpret data. As such, my aim here is not simply to present the validated conclusions, but to tell in part the stories of how and why these individuals did what they did and interpreted as they did. Like many other collective intellectual constructs, science is an echo chamber. A large portion of scientific publication is usually intended to reinforce the already established paradigms. This is even more obvious in the scientific material that is intended for a public audience. In this book, I am relying on scholarly historical references and original sources, while trying to simplify somewhat complex concepts to make them accessible to a wider audience. At the same time, I am narrating a different story that ends in contrast to the current accepted views about the nature of light. The true meaning and implication of the wave theory of light have been gradually dulled and obscured by layers upon layers of conflicting interpretations. To clarify the truth, we need to go back in time to the core of ideas and strip away the layers of confusion one by one. Chapter 3: Democritus and Aristotle's Idea of Light. Plato's allegory of cave is not exactly about the science of light, as Plato was more interested in epistemology, or how we know, than in what we know about the natural world. Still, the mystery of light was present in the minds of ancient sages. From its early impulses to search for truth in the physical reality of the world, humanity though still unequipped with the barest means of experimentation, came across a fork in the path. One path led to the plenum, continuous fullness of the universe. Pilgrims of this path believed there was no gap in the tapestry of the universe, with its infinitely divisible and unlimited variety arising from the interplay of the same unified contiguous element. Pilgrims of the other path believed in atoms and void. Atoms were believed to be infinite in number and various in size and shape, moving about in an infinite void, repelling one another when they collided or combining into clusters by means of tiny hooks and barbs on their surfaces. The void did not require explanation other than providing a place for the unchangeable, uncreated, and indestructible atoms to float in. In our day and age, atomism is well known and established without much dispute, which is a relatively new state of ideology in humanity when considering the long historical developments since ancient times. The true alternative to atomism, which can be called continuum or plenum, is now forgotten and cast out into the shadows of history in such a manner that people are completely oblivious to its existence and its long-lasting dominance. Democritus, who was the champion of atomism, believed that atoms are eternal, but the objects that are made of them are not. Every change in the physical world is caused by atoms moving from one place to another, joining a cluster, leaving another cluster. Sometimes atoms move into enormous whirlpools, forming structures called cosmoi. We might call them galaxies today. These cosmoi are impermanent and will disintegrate in time. And such is the fate of the world and all species in it. Aristotle was the champion of the other side of the argument, and pointed out that atomism reduced all changes in the world to a change of place of some atoms. But what is that place that atoms move within? It is not a problem to imagine the atoms as eternal building blocks of matter, but this view cannot satisfactorily describe the world if the infinite void itself can never be understood. Atoms cannot be the only bearers of beingness, what Heidegger would describe as sign, as there are invisible effects and tendencies that arise seemingly from what was supposed to be the void. The fork in the road of philosophy manifests itself in the divide between physics and metaphysics only if we have already accepted the materialistic view of the physical world that creates a division between beingness and void. As long as the void remains obscure, beingness cannot have distinct boundaries. The same debate was carried over to the description of light and perception. According to Berryman, quote, Democritus' theory of perception depends on the claim that eidola, or images, thin layers of atoms, are constantly sloughed off from the surfaces of microscopic bodies and carried through the air. Visible properties of macroscopic objects, like their size and shape, are conveyed to us by these films, which tend to be distorted as they pass through greater distances in the air, since they are subject to more collisions with air atoms. Close quote. By contrast, Aristotle's explanation of light starts with attention to transparent objects. Everything you see comes to you via a transparent medium like air, water, glass, etc. Transparent objects have some potential in them that opaque materials don't. This potential becomes apparent when a source of light activates them. The colors are properties of this activation. Nothing is visible without light, but light itself is not a thing. It is the activation of a potential. Quote, light is then, in a sense, the color of transparency. Close quote. Our atomists believed that there are only voids and particulates of material existence, and light cannot be ascribed any existence beyond material discharge. Aristotle argued that the source of light, let's say the fire, activates a potential in a transparent environment but does not discharge any material as light. The environment brings this effect to our sense of sight and we see it. Therefore, light is not a physical material, but an activation process in a medium. Aristotle went on to refute Democritus's idea of physicality of light based on his more convincing logical deductions and observations. Because of the prominence of Aristotle and his followers in philosophy and science of the time, atomism remained a secondary idea for generations. Nevertheless, this debate set in motion a pendulum that would swing between these two competing ideas for centuries. Chapter 4: Descartes and Rolle reviving the inquiry. November 10, 1619 was a life-changing night for the 23-year-old French polymath René Descartes. Descartes was on his way home to join the Catholic army of Maximilian in Bavaria after attending the coronation of Ferdinand II, the Holy Roman Emperor. Maximilian was preparing for a long war that would end up lasting for decades. Due to a harsh winter storm, Descartes had to stop in the small town of Ulm near Munich. That night he had three distinct dreams. In the first, he saw himself escaping from the horrors of phantoms who followed him. In the second, he was woken up by a loud noise and saw sparkles of light in the room. In the third, he saw two books appearing on the table, an incomplete encyclopedia and a book of poetry. He was rejoiced by immediately realizing that the books were pointing him towards his life purpose. Modestly enough, he concluded that the dreams were an indication that it was his mission to reform all human knowledge. According to one scholar, quote, what is remarkable about Descartes' dream is not that he dreamed, for even philosophers presumably dream, but that he wrote down a description of his dream and of his interpretation of them, and then kept this record for more than 30 years until his death. What is remarkable, in a word, is that this thinker, who prided himself on his rationalism and who has come to represent, at least to philosophers, the very spirit of rationalism, should have taken his dream so seriously. Close quote. There is an interesting similarity between Descartes' dream and Plato's allegory of the cave that even Descartes himself perhaps did not notice. Descartes' escape from the phantoms symbolizes the horrible turmoil and folly of the time, which is like the state of discord and struggle experienced by the prisoners in Plato's cave. The second dream points to recognizing the false sources of light, or the fire in the cave, which symbolizes the confusing and doubtful beliefs of the time. The third dream gives Descartes hope and shows him the way to grasping the primordial light of truth. 10 years later, Descartes was living in Netherlands, hiding himself from the seemingly unending wars. He dedicated all his time to his theory of metaphysics until a rare phenomena happened in Rome that distracted him and impacted him profoundly. People reported seeing multiple suns in the sky. Such a marvel was not unheard of. It is a relatively rare phenomenon called parahelia, or less gloriously, a sundog. Descartes was fascinated by this event. He abandoned his treatise and instead worked on another project called The World, or Treatise on Light. The Treatise on Light became the most visionary work of Descartes and one of his most influential writings. This event marks the moment that serious inquiry into the nature of light resumed among philosophers and scientists. Descartes was cautious, however. It was very difficult to challenge any established belief, and doing so could be dangerous. Descartes believed that we should start our investigations by things that we can personally examine, relying only on true statements that can be clearly conceived. Thus, he began his treatise on light. Quote, I know of only two sorts of bodies in the world in which light is found, to wit, the stars and flame or fire. And because the stars are without a doubt farther from human knowledge than is fire or flame, I shall try first to explicate what I observe regarding flame. Close quote. Descartes started describing light as consisting of tiny particles being projected from the source of light. It might not be much appreciated these days, but Descartes' method of inquiry was a revolutionary attitude at the time. He went on to explain his idea of the mechanism of light. His approach centered on the organs of sense. Since all of our senses are affected by external stimuli, light must have a physical explanation. He assumes that the flame must emit very tiny particles that are set in motion at great speed and trigger our sense of sight when they reach our eyes. This can be noted as the origin of the corpuscular theory of light in modern science. Rolle was a French gentleman who followed Descartes and popularized the system of inquiry of nature by means of experiment and observation. He held weekly meetings at his house in Paris, demonstrating physics experiments and discussing them with the audience. These meetings grew in popularity and paved the way for popular interest in physics. He also had to refute Aristotelian philosophers and assure the Church that they were not promoting materialism. Roholt built on Descartes' foundation by adding his own observations about light and seeking all possible sources that could help him understand it a bit better. Roholt describes an incident when he was tantalized by a stone that shined in the dark and used the opportunity to contemplate the nature of light. Quote, "Though we have no jewels which shine in the dark, yet we have a stone that is truly luminous. This stone was accidentally found by an Italian chemist near Boulogne in a hollow place caused by a torrent. After having put it into a fire for 6 hours, he took it out and let it cool, and when it had been exposed to the light of the air for some time, upon carrying it afterwards into the dark, he first perceived it to look like a fire coal, covered over with few ashes. I have seen some shine near half a quarter of an hour, after which their light vanished, but by exposing them to the light of the air for a short time, we could make them shine again." Roald thought that the stone must have some porous structure that keeps the light particles for several minutes and then pushes them back out. This must have also explained to him the mysterious quality of transparent objects. They have pores that allow the subtle matter of light to pass through them in straight lines. Opaque materials either don't have these pores, or light can't go straight through them all the way. In our age of readily available scientific knowledge, we find it easy to dismiss theories of this kind, but we can do so only because of our access to a body of knowledge whose foundation was laid by thinkers like Roald and Descartes. Laying aside your textbook knowledge, how would you consider this seemingly simple puzzle of the glowing stone, of opaque and transparent substances? How does light pass through certain objects? How would you explain it? Roald was attempting to explain something humanity had taken for granted throughout recorded history, and that attempt alone was revolutionary. Roald's system of natural philosophy was translated in Latin and English and remained an influential textbook for 50 years. His theory was first overshadowed by Huygens' wave theory of light and then published again about a century later with complementary footnotes reaffirming its truthfulness, cited from Newton's corpuscular theory of light, also called corpuscularism. Chapter 5: Huygens' Wave Theory of Light. Around the mid-17th century, knowledge of light mostly consisted of optics. There were well-established laws and geometrical measurements about the path of light. The most important ones were: light moves in a straight line. When reflected on a flat surface, its angle of incidence and reflection are always equal. When light enters water or glass from air, there is an apparent and sudden change in its trajectory. The angle of incoming light to the surface is different from the angle of light leaving on the other side. However, the ratio of the sine of angles is a measurable constant for any given material. This is called refraction. In addition to these phenomena, it was well observed that beams of light can pass through each other in different or opposing directions without affecting each other. But there was still not much known about the mechanism of light. Its behavior was observed, but the question remained, why does light behave this way? Christian Huygens, born on 14th April 1629 and died in 8th July 1695, was a Dutch scientist and personal friend of Descartes, who took on the inquiry about the nature of light by making detailed experiments and accurate observations. He deployed a theory that could geometrically explain the reflection and refraction of light. It is still very early in our journey of discovery about light, but Huygens' simple and elegant description is the key to understanding all of this book. Here is the core of Huygens' theory from his Traité de la Lumière. First, light must be associated with some kind of physical movement because its generation is associated with heat and movement such as fire. Also, when we concentrate the sunlight in a spot, it can generate a large amount of heat, which has to be some form of mechanical movement. Second, the movement of light is not similar to movement of particles, projectiles, or arrows, because light propagates in all directions from the source with a great speed, and if it consists of particles, the two beams of light passing in opposite directions should have disturbed each other, but they don't, so light must be moving in a different manner. The closest natural phenomena that can help us in understanding the behavior of light is sound. Sound propagates through the air in all directions from the source, and different sounds can pass through each other. Huygens reasoned, quote, "I call these waves because of their resemblance to those which are formed when one throws a pebble into water, and which represents gradual propagation in circles, although produced by a different cause and confined to a plane surface." End of quote. For the wave theory to be viable, it is necessary that light propagates at a constant speed, just as sound does. Then the next big question at the time was whether light has a speed or happens instantaneously. How fast does it move? Is there a way to estimate it? In all experiments that were possible at the time, light's travel seemed to be immediate. Descartes studied the timing of a lunar eclipse to see whether the shadow of the earth appeared with a measurable delay on the moon. He couldn't measure the delay. The distance weren't long enough and measurements weren't accurate enough. Fortunately, Huygens had already contributed to the understanding of movement of pendulums and had patented the most accurate clock of the time, which remained unrivaled for the next 300 years. He had also developed some of the most accurate telescopes that allowed him to observe the shape of the rings of Saturn and discovered Titan, a satellite of Saturn, for the first time. Was this amount of ingenuity enough for humans to estimate the speed of light? Yes, it was. There is a figure of its description demonstrating the position of Sun, Earth, Jupiter, and its moon, as was used by Romer for calculating the speed of light. Source is Huygens' Treatise on Light. In 1676, the Danish astronomer Ole Rømer (1644–1710) successfully proved that light has a speed and calculated it with impressive accuracy, using only a clock and a telescope. He observed the innermost satellite of Jupiter, and noticed that this satellite enters the shadow of Jupiter and comes out of it in precisely observable periods of 42.5 hours. In the figure above, A is the position of the Sun, F is the position of Jupiter, and the satellite passes from point G to H, which is observable from the Earth at point B. He realized that the satellite of Jupiter works as a cosmic clock, and if he kept measuring these periods 30 consecutive times, the Earth would move from point B to point C. The light has to travel an additional distance of mc to reach the Earth in a new position, which is a significant amount of distance further from the first observation station. He kept measuring these time intervals for 10 years. The time differences between periods of Jupiter satellite appearances were consistently measured to be about 10 minutes, and at the end, Romer calculated the speed of light to be at about 600,000 times greater than the speed of sound. Taking the speed of sound to be 343 meters per second, he calculated the speed of light to be in the order of 200,000 kilometers per second. This is incredibly fast, of course, but what mattered the most was the realization that light speed is finite and measurable. Sound propagates in air, and light propagates in a different medium that Huygens called ether. Huygens knew that air consists of small particles that move around rapidly and collide with each other, similar to billiard balls. Then he concluded ether must consist of much smaller and much more compact particles that are endowed with a hardness almost perfect and with an elasticity as great as we please. End of quote. The wave propagation in an elastic medium is the only viable explanation for the uniform and non-diminishing speed of light. Again, if light was made up of shooting particles from the source, they would have lost their speed over very long distances and slowed down eventually. Quote, if indeed one looks for some other mode of accounting for the gradual propagation of light, he will have difficulty in finding one better adapted than the elasticity to explain the fact of uniform speed. End of quote. Huygens. An important concept in understanding the propagation of transverse waves is the fact that direction of propagation has nothing to do with the actual movement of particles of the medium in that direction. For example, when we make waves on the surface of the water, the waves propagate on a plane parallel to the surface, but water particles only go up and down. This means that if we generate waves on the surface of a stationary pond or on a calm stream that is gently moving, we see no change in the total flow of the water. Regular light does not affect the large-scale motion of the ether, just as gentle music does not generate hurricanes. The opposite is also true, meaning that a wind does not change the speed of the sound that passes through the air. Huygens understood this property and mentioned it in his treatise. Quote, "It must, however, be added that although the ether particles are supposed to be in continual motion, and there is much evidence for this view, the gradual transmission of the waves is not thus interfered with, for it does not consist in a translation of these particles, but merely in a small vibration, which they are compelled to transmit to their neighbors in spite of their proper motion and their change of relative position." End quote. Huygens' geometry of light. What has been mentioned so far is not yet what Huygens himself contributed to the wave theory. Before Huygens, Robert Hooke (1635 to 1703) has already proposed a wave theory for light, but he could not describe the three known aspects of light: propagation in a straight line, reflection, and refraction. What distinguishes Huygens' theory from everyone else's is his elegant geometry construct. Huygens' simple geometry elegantly explained all known properties of optics. This section is slightly math-heavy and may require some knowledge of geometry and perhaps some paper, pen, ruler, and compass if reader wish to follow the proofs. The idea of geometrical progression of light follows from the line of thinking in the previous section. Particles of ether only have to transmit their tiny vibrations to their neighbors, nothing else. Let's assume that once excited, every ether particle translates its excitation immediately in all directions, and light will be transmitted where all the excitations overlap. Additionally, the translation of excitations in a uniform elastic medium happens at constant speed. We only need a ruler and a compass to explain the rest. I will skip the few next pages because they require geometry, and I pass to page 38 and continue after the explanation of the geometry. If you tried to explain refraction by imagining particles of light passing from one medium to another, you would arrive at a contrasting conclusion about the speed of light. Since light particles are moving at great speed, a sudden change in their direction must indicate an exchange of momentum. When light is perpendicular to the surface of two mediums, it keeps moving into the second medium on the perpendicular line. When a light beam comes in with an angle to the perpendicular line at the surface of air and moves into the glass, its angle gets closer to the perpendicular line. When it passes from glass to the air with an angle, it is deflected further away from the perpendicular line. The logical conclusion made by Descartes, Roald, and Newton was that air must exhibit more resistance to the movement of the light than glass does. That is what an intuitive mechanical approach to light corpuscles logically arrives at. Thus, the wave theory and corpuscular theory of light came to the exact opposite conclusions about the relative speed of light in air versus glass. This problem remained undecided for about another 100 years until the direct measurement of the speed of light became possible. Today it is common knowledge that the speed of light is higher in the air than in the glass, but corpuscular theory of light can't be readjusted to accommodate this fact. Even if there were an agreement about the slowdown of speed in a more refractive environment, the corpuscular theory of light still has to explain the sudden changes in the speed of light from one medium to another. Imagine light particles entering a bar of glass from the air and slowing down for any reason. The corpuscles continue with a lower constant speed inside the glass. What enables these particles to regain their original speed when they exit on the other side of the glass back into the air? The same mechanism that has slowed the particles down in the glass must be reversed to accelerate them again upon their exit. The inquisitive mind of Huygens didn't stop at explaining the refraction. He wondered about the nature of transparency. It is easy to accept that air is transparent because it is made up of sparse material particles and ether fills most of its volume. The air particles are so sparse that they do not pose any obstruction to the propagation of light in ether. It can be observed that the refraction index of air depends on its density. The lower layers of atmosphere have slightly higher refraction indices, leading to observable atmospheric refraction phenomena. What is more difficult to explain is the transparency in solid objects, such as glass or crystals, and the mechanism that causes the light to slow down in them. A special type of crystal offered a valuable clue to Huygens. Iceland crystal was a transparent crystal of calcium carbonate, originally brought from Iceland. When a single ray of light is beamed at the surface of this crystal, it splits into two refracted beams inside the crystal. One of the beams follows the regular refraction properties, but the other beam proceeds at an irregular angle. Even when the light is entering perpendicular to the surface of the crystal, the irregular refraction creates an angle with the perpendicular line. Huygens explains this by assuming that the irregular beam propagates in ellipsoids instead of circles. He managed to calculate a satisfactory way of describing these angles by knowing the major and minor axes of the ellipses with respect to the geometry of the crystal. He concluded there are at least two types of movements inside the transparent material. The regular one propagates in spheres, but the irregular propagation follows some preferential direction depending on the internal structure of the crystal. After writing these explanations, Huygens observed yet another unexpected behavior of the light when he passed the regular and irregular refraction rays through a second crystal of the same type. If crystals are aligned with their internal axes being parallel to each other, then the refracted rays of the first crystal go through the second crystal without splitting. A regularly refracted ray only has regular refraction, and an irregularly refracted ray only has an irregular refraction in the second crystal. But if the internal axes of the crystals are perpendicular, then regular refraction of the first crystal goes through an irregular refraction in the second crystal, and vice versa. This was an admirable level of accuracy and attention to detail on the side of Huygens. It is amazing how much was discovered about the nature of light within a few decades of the 17th century. Huygens turned Descartes' dream into a reality. The intellectual legacy of mankind is forever indebted to the creativity, craftsmanship, detailed observations, mathematical ingenuity, logical deductions, and many hours of hard work from intelligent and inquisitive minds such as Huygens. If there is one character that has perhaps come close to Huygens in his search for the nature of light, that must be none other than his contemporary Isaac Newton.